Good day, netizens. So today we'll be talking about the effective density of states prepared by yours truly. Yes, yours truly. So first, the density of states in the conduction band. We already are kind of familiar with this equation. We found this in our previous module 4, dun sa band structure natin. The density of states in the conduction band is equal to V, where V is the volume, times 2 pi squared, over 2 pi squared, sorry, times 2GD times 2ME over each bar squared all over, raised to 3 halves times E minus EC raised to 1 half. So, itong formula na to, same lang siya nung dati natin ginamit except for one additional term, itong GD term na natin dito. Yung GD term natin dyan, this is what we call your degeneracy. This is the degeneracy factor. And we'll be discussing this in the succeeding slides. So, ito lang yung nabago natin mula dun sa dati. So, one note din, for ME, yung ME natin, alam natin from the previous slides, we can get it by getting the second derivative and using our equation. But usually, tabulated na yung effective mass ng ating electron sa mga crystals. So, meron yan tabulated yan sa mga appendix and na-measure na natin dati or na-measure na nila yung transverse and longitudinal electron effective masses. And to get the effective mass that we need to get for our equation here, ME, we just get yung MT and ML from our reference and just use this formula to get etong effective mass na ito. So no need to get the second derivative anymore. Anyways, now let's go back to the degeneracy. Ang degeneracy natin, na encounter natin yan before, yung GD, this is the degeneracy term for our energy level. So in this case, degeneracy term for the bottom of the conduction band. But what is degeneracy? Yan, what is degeneracy? An energy level is said to be degenerate if it corresponds to more than one measurable state of the quantum system. This is just a fancy way of saying, basically, ilang k or wave number or wave vector, wave number slash wave vector corresponds to an energy E in our first Brillouin zone. So if you didn't get that, I think it will be better if we go into some examples like this. This is gallium arsenide. Or more specifically, ito yung band structure ng gallium arsenide. From the band structure, we can see that gallium arsenide, let's zoom in. Gallium arsenide is a direct gap semiconductor. Bakit siya direct gap? Kasi same lang ng K nag-occur yung bottom of the conduction band and top of the valence band. So hopefully, ayun siya. So this is a direct gap type semiconductor. The bottom of the conduction band will then occur at point gamma, or at this point here. If we look at the first Brillouin zone, this point here is yung center ng first Brillouin zone mo. And this will become, since nasa center yung gamma point na yan, meron lang tayong isang point na ganyan. There's only one point in the FBC, the first Brillouin zone, na ganito, na point gamma. There's only one point. So for gallium arsenide, the degeneracy is equal to 1. Or dati, yung kinuha natin sa module 4 dati, wala na tayong consider the degeneracy na built in na natin yung 1 kasi direct gap semiconductor yung consider natin dati. Now let's look at other examples. Now let's look at silicon. For silicon, the absolute minima of your energy band or energy band structure of your conduction band occurs at K is equal to 0.82 pi over A, or in this point here. Ito yung absolute minima natin sa silicon. This occurs at this point along the direction, along the direction delta. Dito. Siya. When we plot this into our first Brillouin zone, makita natin it will correspond to this point. Itong point na to. This is along the delta direction from our band structure. Ito siya. Nasa delta direction siya. From gamma to x. Gamma to x. Along the delta direction. Pero makita natin, itong point na to, this is not unique for this direction. Makita natin, there are equivalent points here and here. And actually, 6 yan. Meron pa yun sa baba, sa likod, and sa isa pa ng likod. There are 6 equivalent directions. There are 6 equivalent delta directions now in silicon. Now, let's look at germanium. For germanium, the absolute minima now occurs at 8 equivalent L points, or somewhere here. It's here. Ito yung absolute minima ni germanium sa conduction band niya. If we plot this again in our first Brillouin zone for germanium, makita natin it will be at this point. Ito. And since meron tayong 8 phases na ganito sa first Brillouin zone natin, 1, 2, 3, 4, 5, 6, 7, 8, may 4 sa likod na hindi natin nakita, there will be 8 equivalent L points na pwede natin consider. So given that, we can then get the degeneracy for silicon and germanium. First, for silicon, since the conduction band minimum occurs at K is equal to 0.82 pi over A, along the delta direction, and there are 6 equivalent delta directions, we'll get that the degeneracy of the conduction band minimum is 6, or GD is 6. Because 6 equivalent directions, the degeneracy is 6. Kasi 6 na K meron tayo. Simple? Yes. So 6 equivalent have a GD of 6. For germanium naman, since the conduction band minimum occurs at L, and there are 8 equivalent L points, the degeneracy of the conduction band minimum is 4. Bakit 4? 4? Tama ba yan? Yes, tama yan. So, even though there are 8 equivalent L points in germanium, makita natin that the degeneracy of the conduction band minimum will be 4. Now, let's look back in the first Brillouin zone of germanium. So, bakit 4 lang yung degeneracy natin for germanium? Bakit 4? Kung 8 naman yung nandito. Why 4? Because this L point here, this is shared by 2 neighboring Brillouin zones. Remember, yung first Brillouin zone natin, this is a unit cell in the reciprocal space. And may mga katabi yan, efficiently packed yan, space filling yan, yung unit cells niyan. And this point L here, this is shared by another unit cell na ganito yung shape, and shared tong point na to by the 2 first Brillouin zones. By the 2 neighboring Brillouin zones. So, mangyari, since meron kang 8 points na equivalent sa FBZ, but nakita natin na shared siya ng dalawang first Brillouin zone, yung contribution of each point is just 1/2. 8 times 1/2, this is just equal to 4. And this is your degeneracy. So now let's take another example. So I'll let you try if you want to. So example, now let's take gallium nitride. Gallium nitride has the wurtzite crystal structure. Wurtzite. The conduction band minima happens at K. Ito yung KX, KY, and KZ natin. At K is equal to capital K, or this point here. What then is the degeneracy factor GD for this gallium nitride, or for the conduction band minima of gallium nitride? So first, let's look at the symmetry of your Wurtzite structure. And so, if you want pala, you can pause this to try it yourself. Anyways, now, let's look at the symmetry of the Wurtzite structure. This is a hexagon. And yung top view dyan, parang ganito. Yung K natin, this occurs at the corner of your hexagon. Corner. Ilan ang corner ng hexagon natin? 6. There are 6 corners or 6 equivalent key points. So, 6 yan. 6. But, each of these corners will be shared by how many first Brillouin zones though? So, each of these edges or each of these corners, tignan natin. So, kung hexagonal yan, meron ka pang isa dito, and isa dito. So, kung ito si K, kita natin there's 1, 2, 3 first Brillouin zones that share that corner or that point K. So, each of these points will have then a contribution of 1/3. Or, we'll see that the degeneracy factor will be equal to 2. 6 equivalent K points, the first Brillouin zone, shared by 3 first Brillouin zones. 6 divided by 3, you get 2. So, hopefully, alam nyo paano nyo siya kunin. And, yeah. So, the density of states for the valence band, meanwhile, is this equation. So, similar lang siya sa conduction band, but now we can see wala na tayong GD. Wala na tayong degeneracy. This is because the degeneracy of the conduction band, the valence band maximum, is always equal to 1. Kanina meron tayong formula ng GD. Wala na siya dyan. Equal to 1 na lang siya. There is no degeneracy here since yung value nung top of the valence band is always at the zone center or at K is equal to gamma. Yung sa center ng conduction nung ating first Brillouin zone and wala naman siyang ibang symmetric points pa. Kasi siya na yung pinakagitna. Another thing to note here is meron din tayong tinatawag na MH. Yung MH naman, this is just like ME, but this is the whole effective mass. So, dapat ito is valence band, and valence band. Anyways, so the whole effective mass naman, tandaan natin sa ating first Brillouin zone, or sa ating band structure for our holes, meron tayong tatlong 1, 2, 3 na subbands. And dalawa dito sa subbands na to, yung heavy hole and light hole, both are degenerate at the top, dito sa taas. Both have the same energy at the top of the valence band. So the heavy hole and light hole bands have the same energy at K is equal to 0, K equals 0, or K equal gamma. And alam natin yung curvature niyan, meron yung heavy hole and light hole. So to get just the effective hole mass, MH, we just use this formula. We have the mass, effective mass of the heavy hole, and the effective mass of the light hole. Use this one, you get the MH that we need to use for our density of states for our valence band. The density of states though only tells the allowed energy states for a unit interval of energy, or basically kung ilang electron energy states or ilang places na pwede tayong pumasok ng electron natin na pare-pareho lang energy. But what now if we want to know the concentration of electrons in our conduction band? We must then turn back into our Fermi-Dirac distribution. We multiply our density of states with the Fermi-Dirac distribution to get the number of electrons per energy level. Then we can integrate that from the bottom of the conduction band, integrate it from EC to infinity to get the total number. So this expression here would give you the total number of electrons in our conduction band. And to get the concentration, we just get the number divided by the volume of your crystal. So we get this one. This is your concentration of our electrons. So we can further expand yung ating concentration of electrons. So meron naman tayong expressions for GCE and FE. We'll have N is equal to 1 over V EC to infinity. Yung GCE natin, or the density of states for the conduction band, we found that is equal to V over 2 pi squared GD 2ME over H bar squared 3 halves E minus EC 1 half. Then yung ating Fermi or yung ating electron distribution function, FEE natin, this is 1 over exponential of E minus EF over KBT plus 1. Ganyan. So, upon simplifying this expression, how simple we can get it, simplifying in quotes, we get N is equal to GD over 2 pi squared 2ME over H bar squared 3 halves EC gamma, then ito na integral E minus EC is to 1 half over exponential of E minus EF over KBT plus 1. So ito ay isang napakalupit na equation, sinusumpa ng mga estudyante, pero hindi naman natin kailangan ito, yung derivation, just for FYI. So applying a changed variable, we can express this term here, E minus EF over KBT. We can express this one as Y, and we can express dy is equal to 1 over KBT dE. Wala natin yung first derivative nito with respect to E. The integral, this one then becomes K BT is 3 halves 0 to infinity. So nagkaroon tayo ng change in the limits. Y 1 half over exponential of Y minus EF minus EC over KBT plus 1. So I'm sparing you most of the math for this one. Trust na lang natin siya. Then, we can define yung ating Fermi-Dirac integral. So we can define what we call the Fermi-Dirac integral, usually represented by F 1 half of X is equal to 2 over square root of pi 0 to infinity of Y 1 half over exponential of Y minus EF minus EC over KBT plus 1 dy. So nakita natin, if nakita nyo pa yung sinusulat ko, ito at saka itong Fermi-Dirac integral natin, similar sila ng form. Sa dy pala. So similar sila ng form because this is actually a form of the Fermi-Dirac integral. So pwede natin itong gawing Fermi-Dirac integral using x is equal to EF minus EC over KBT. This previous integral then becomes, so itong nasa taas, see? So ito, this will then become biging KBT is 3 halves times square root of pi over 2 para ma-account tong term na to. Then we will have itong nasa loob, this is just F 1/2 of EF minus EC over KBT. So, yung integral natin kanina, nagawa natin, ganito na lang siya. Then this one, we can bring this back into our equation here. Dito. Balik natin siya dyan. And we will get that our expression for n, n is equal then to GD over 2 pi squared 2 me over h bar squared 3/2 kbt raised to 3/2 square root of pi over 2 times itong f 1/2 ef minus ec over kbt. So excuse my very, very terrible handwriting. Then we can express h bar squared, or h bar is equal to h over 2 pi para lang magkaroon tayo ng cancellations and maging 3/2 yung something. Or h bar squared, 1 over h bar squared is equal to 4 pi squared over h squared. Then we'll get our concentration of our electrons for emphasis. Laki natin yung font. Yan. Sorry, so laki dapat. 10. We'll get that n, or our concentration of electrons, will be equal to 2 GD. Then we can put this all in one expression. 2 pi kb t me over h squared raised to 3/2. So, kailangan natin transform ito para mapasok natin lahat sila sa raised to 3/2 f 1/2, or the Fermi dirac integral, ef minus ec over kbt. And ang maganda dito, or ang hinahanap natin, kaya natin ito kinuha, this term here, itong term na yan, this is your NC, where NC is the effective conduction band density of states. So this term here, itong nakalagay dito, this is NC. This term is called the conduction band density of states. And the effective conduction band density states is just the thing, or the term, that we multiply to our Fermi dirac integral to get the number of electrons, or the concentration of electrons in our conduction band. This simplifies our equation because itong Fermi dirac integral natin, kahit medyo mahirap siyang tignan, tabulated naman yung values niyan in standard tables. And also, yung ating Fermi dirac integral, if it can reduce to a simpler expression when in a special case. So, yung special case na yun is when we are in a non-degenerate condition, or pag tinatawag natin na meron tayong non-degenerate na semiconductor. Pag degenerating semiconductor natin, essentially, yung ating distance of the EF, so kunyari, ito yung conduction band, and ito yung Fermi energy, EF, Fermi energy. So, yeah. The distance between the Fermi energy and your conduction band minimum, yung distance na yan, this should be greater than kBT, or the thermal ionization energy for that specific temperature. Ang maganda sa atin, non-degenerate pala. non-degenerate semiconductor. Ang maganda sa atin, most of our cases are of this non-degenerate semiconductor. And in that case, yung Fermi-Dirac integral natin, this just reduces to exponential of EF minus EC over KBT. So ito, F1 half naging exponential lang siya. It's the reducing term. Then, for a non-degenerate semiconductor then, we'll get N is equal to NC exponential of EF minus EC over KBT. So that is the case for our for the concentration of electrons in the conduction band for a non-degenerate semiconductor. We have just a simple equation here. Ito na siya. So kaya lang natin kinuha yung pagkahaba-haba para makuha natin itong effective density of states conduction band. Kasi mula dito, and knowing the Fermi energy and the conduction band and the temperature, we can get the concentration of electrons in our conduction band. So usually, itong NC na to, this is actually a material property in quotation marks. Basically, meron yan, kunyari, for 300 Kelvin, alam mo yung silicon mo, ganito yung condition, makuha mo yung NC niya. Hindi lang siya. So, NC, again, is ito. This is our effective conduction band density of states. For the valence band, we can also have the same expression, which I will just leave in the module for you to read. But similar na expression niya, iba naman tayo, NV naman. And yung NV na yon, that is just multiplied to the Fermi-Dirac integral to get the concentration of holes in the valence band. And upon the non-degenerate case, we also have yung ating simplified expression. So hopefully nakatulong tong videos na to. Mahaba na siya and I'll stop here. So thank you for listening.